So thanks to the organizers for the invitation to speak at this summer school. Thank you very much. And thank you to Frederick for already introducing the general pipeline on TDA and Frederick was referring to many things that I will tell you. I'm not sure I'm up to the task, so I try to go back to a little bit to the theoretic underlyings of persistence theory. So the general persistence pipeline, maybe we can describe it in that way, as it is given here. Namely, we start with a data set, as we have said, and to this data set we associate some filtration, and the filtration allows me to compute a persistence module. So I first want to talk about that quickly, and I really want to go into the details of this barcode and how to use this elder rule and those things. And what Frederick has told us so far, or what we have been seeing so far, is about one parameter persistence theory. I also would like to talk about two multi-parameter persistence theory and what can be done in this case, or why there's a difference between these two situations. So that's the first thing I want to point out. A persistence module, if you go to papers on TDA, on persistence theory, a persistence module really is a functor from a poset into the category of vector spaces. So we had some discussion when we were preparing for the summer school, what is the common denominator of the background of the participants? And the conclusion was, I cannot assume too much. Yeah. And so I can ask the same question that you hear in Frederick's lecture. So who among you is comfortable with functors and categories? These are many people. That's very good. Who is not comfortable with functors and categories? These are also a lot of people. And who didn't say anything? Thank you very much. So I hope we cover everybody. So what I thought is I will not give an introduction to category theory. This takes too long, and what's the point of this? Yeah, I mean, we only want to use the language as it is necessary for that context. So I try to develop a little bit the language of functors as it is needed for our purpose. But I will basically, I'm trying to give you the theoretical underpinnings of the theory using linear algebra, based on linear algebra, because everybody knows linear algebra. That's the basic assumption. Yeah. And I was going to the archive this morning, as I often do, and check for new papers. And this is not what I wanted to show you. I was going to the archive and check for new papers, and what I see, there is a paper appearing this morning on topological data analysis via undergraduate linear algebra. So they could have published this 1 month ago. They would save me a lot of time. So maybe this is what I'm going to do. I don't know. I had no time to read it. But that's the plan, to present everything, the theory based on linear algebra. Okay, so that's good. Okay, fine. So let's go to the first step, and there is this picture that we have seen already a couple of times. So you start with some finite set of data in some d-dimensional vector space. And we want to analyze this using topological data analysis. So we want to analyze this by computing homology of this data set. Now, the data set per se is not interesting. As we heard, it's a discrete topological space. So what we're going to do is around each point, we put a ball of some radius epsilon, and then we consider really the union of these balls of radius epsilon. So here in this picture, you see the union of the balls of radius epsilon. By the way, when I draw a point, I mean, it has already got some radius. You see this one? I mean, a point, really, you don't see it. I mean, what we draw is already a disk. So, I mean, we just extend this notion to have disks, balls of a larger radius. We take the union of all of those and call this one here d epsilon, right? So for every epsilon, we get one topological space. And then we compute homology of that topological space, the piece homology 0, 1, or maybe 2 homology of that space. So there's a link. I should go to GeoGebra. Let me try to do that. Can I do it? I would like to go to GeoGebra. So here's my point cloud. It looks like a A, B, C, D. It looks like a circle. You see what I do? And then I want to increase the radius around these points. Yeah, this is good. So this is inherently a dynamical process. So I want to give you a demonstration of the dynamics for once. So you can increase the radius. And if you increase a little bit, some of those balls will start to connect. They intersect, right? And then we go further. They will intersect even more until we see that, whoops, here, you see some H1 appearing. Yeah, I mean, there's a non-contractible circle. So we see some H1 appearing. And if we increase the radius further, that's hole in the middle will become increasingly or decreasingly small until it disappears. Yeah. So there's a certain period where an H1 is measurable, is visible in that union of balls. And that period where the H1 persists, that's gives rise to the name of persistence, modular persistence theory. Some topological feature persisted for some extended range. Okay, so that's really what we are going to talk about here. That's good. Yeah, and so for every epsilon, we have such a topological space. We associate to this the homology group or the homology space, one for every epsilon. So we really get a map for every non-zero, for every positive real number. We get a vector space. To each epsilon, we associate the homology of that topological space. Okay, and the spaces here, they are filtered. I mean, if you increase epsilon, then the union will become only larger. So for smaller epsilon, that space del d epsilon will be contained in d epsilon prime. And now this construction, computing homology, will compute a vector space for every epsilon. And the inclusion here will translate into a linear map between these two vector spaces. Yeah. So those who know what I'm talking about, taking homology is a functor, but it's not an exact functor. So the inclusion here will not necessarily turn into an injective linear map. It's just a map. It's a linear map of vector spaces. Okay. And so we get a system of linear maps between vector spaces, one vector space for every positive real number. And this is what is called the persistence module. Okay, so this is what we want to study now in detail. What am I talking about? What is a persistence module in general, and so on and so on. So in particular, what does this one here mean? I will spend the next couple of minutes just defining those notions. Okay. Sorry, no. this one. Yeah. Okay, so let me start talking about posets and representations. Yeah. A poset, we all know what is a poset. Poset is a partially ordered set. So I have a relation which is reflexive, antisymmetric, and transitive. Partially ordered set. Examples of posets are, as we just have seen, the positive real numbers. Yeah. They form a poset under the usual relation one number is smaller than another number. Okay, so this poset is a very particular poset because it's totally ordered. It's not a partially ordered set, it's actually a totally ordered set. Any two real numbers are comparable. This need not be true in general when we consider posets. So for instance, let's look at a square. So this will appear in two-parameter persistence theory. Let's look at R squared and how can we order 2 points in R squared? We say x with coordinates x1, x2 is smaller than y with coordinates y1 and y2 when both coordinates are ordered. So x1 smaller than y1 and x2 smaller than y2. So in pictures, I mean, here we have R squared, and then that point x will be smaller than that point y if it's kind of to the up and to the right. Yeah, so north, west of x, everybody there will be larger than x. Okay, so this is a nice partial order. It's not totally ordered. For instance, these 2 points are not comparable. Yeah, I mean, if I take the point 1, 0 and the point 0, 1, none of them is larger or smaller than the other. So it's a true poset, a partially ordered set. Okay, so this is what we are talking about. And quivers. So why do I come up with quivers now? We talk about posets, right? But I want to talk about quivers, and quivers will appear very soon into the picture. And also I received my mathematical education studying quiver representations. I did my degree in Zurich under the supervision of Gabriel, who introduced quivers to mathematics. So that's my mathematical kindergarten. Therefore, let's talk about quivers. A quiver is just a bunch of arrows. Do you know what a quiver is? What the English word quiver means? I mean, it's where you have a bunch of arrows in your back. Okay, so a quiver formally is given by a set of vertices and a set of arrows between those vertices. And examples of quivers, they will appear several times. So some simple quivers, they come with names. Yeah, so a quiver of type AN, linearly oriented, is a quiver that has this shape. Yeah, points 1, 2 up to n, and arrows going up 1 to 2, 2 to 3, and so on. A quiver of type A3 is generally a quiver with 3 vertices, where the vertices are kind of in a line, yeah, but they need not be linearly. I mean, there can be an arrow from 1 to 2 and one from 3 to 2 backwards. So this is allowed. This is a quiver of type AN. And there are quivers of other types. Some are called quiver of type D4, like this one. So this is quivers. Good. Yeah. Who has heard of a quiver mathematically? Who did not hear the name quiver mathematically? Good. A quiver is just a digraph, an oriented graph, right? We could call it an oriented graph. In general representation theory of quivers, we do allow quivers having loops or quivers having multiple arrows between vertices. So it's depending which book you look at, it would not be a quiver, it would not be a graph, it would be a pseudograph. It's a directed pseudo. Give me a break. It's a quiver. Okay, so we have one word for this. That's okay. A bunch of arrows. That's what we have. Good. Okay, so quivers. We are comfortable with quivers. And why do I talk about quivers? So here's my slide to motivate. We really are interested in posets, P. When I have a finite poset, to the finite poset, I can associate a Hasse diagram, which is oriented, so it's a Hasse quiver, yeah? So the Hasse quiver of the poset has as vertices the points of the poset, but I do draw an arrow only when I have an order relation that cannot be refined, when I have a minimal order relation, a cover relation, or however you want to call it in your combinatorics class. Yeah. So for instance, when my poset P is just the natural numbers 1 to n with the natural order, then the Hasse quiver of that poset is 1 to 2 to 3 up to n. Yeah, so these are the minimal relations, these are the arrows, and there's more relations by transitivity of the partial order. There's more order relations, like if 1 is smaller 2 and 2 is smaller 3, 1 would also be smaller than 3. But in the Hasse quiver, we do not draw this information. I mean, this is encoded in the transitivity. We don't need that. Yeah. So we just draw the minimal necessary information, those order relations. If I have now, this is like a discrete version of a few points in my poset R2 that we had a minute before. Yeah. So I can take the poset whose Hasse quiver is this one. One goes to 2 and one goes to 3 and both go to 4. And this includes, that's the Hasse quiver of a poset. So that includes by transitivity also that 1 would be smaller than 4 and 1 would be smaller than 5 and 1 would be smaller than 6. So for finite posets, it's totally sufficient if I give you that Hasse quiver, and this uniquely determines the partial order. That's okay? Yeah?
Like in different directions, we can take different numbers of steps to reach a particular.
I don't need a lattice. I don't need any rank function. I mean, I could have a, 1, 2, 3. This one, this is a perfectly fine poset. Yeah. Okay. So posets, when they are finite, are uniquely determined by their Hasse quiver, and therefore I have a good right to talk about quivers to you, which I'm very happy about. That's good. Shall we go back to our very first slide here? There was a poset appearing the real numbers, as a poset. So this is now an infinite poset, as you would agree. The real numbers are an infinite poset, so there's vertices x and y and so on. And what is the Hasse quiver of this poset? It has got no errors. There's no irreducible, there's no minimal relation. No real number has an immediate successor. Yeah. So the Hasse quiver of this poset is not very interesting. It's of no use. Yeah. So this Hasse quiver is very good when we have finite posets. For infinite posets, we need to adopt the language of posets. That's why I talk about posets in the first place. Okay. Good. So let's come back to where are we? The Hasse quiver. Now let's talk about representations. This is really the reason why Gabriel introduced quivers into algebra, to talk about representations of quivers. You may have seen representations of a group. We represent group elements by matrices, invertible matrices, because every group element has an inverse, such that the system of matrices follows the group multiplication. So we represent objects by things coming from linear algebra. This is the very idea of a representation. So the assumption is we know linear algebra, we have some abstract object, we represent it using matrices. We're going to do the same thing for quivers. Yeah. So given a quiver, we want to represent the quiver using linear algebra. Using linear algebra means I have to fix my field. So let's fix a field, let's fix a field K. I call the field K like Körper because I'm German. And in TDA, often you use the field with just two elements because it's very easy to do computations on a computer. Yeah. In representation theory, we often like an algebraically closed field like the complex numbers. You choose your favorite field, and then a representation M of the quiver Q is when I map the quiver into vector spaces. What does that mean? For every vertex of the quiver, I give myself a vector space, mx. For the vertex y, I give myself a vector space, my. And when there's an arrow from x to y, then I give myself a linear map from the vector space mx to the vector space my. So really the datum of the bunch of arrows I represent it in terms of linear maps between vector spaces, the same configuration. Okay, so this is what is called a representation of a quiver. And by rep q, I denote the total collection of all representations possible of the given quiver Q. Yeah. If you like, you can call this the category of representations. And they are called, and they are finite dimensional representations because I restrict myself here to finite dimensional vector spaces. Yeah. Because the homology spaces that we're going to compute, they will all be finite dimensional if we come from a finite set of data. Okay. So this is the notion of representation of a quiver. For always give an example. So here's my quiver, type A3, 1, 2, 3. Here's my representation. I give myself a vector space for each vertex, k square, k. And in between them, I give myself two linear maps, which are here presented by matrices, this one and that one. This is a perfect fine representation of that quiver. Good? Questions? The representations, the category of representation is an abelian category, yes. And even the subcategory of finite dimensional representations is still an abelian category. So you are in the best world possible. That's good?
Yes, they are.
No, here I have one linear map. I give myself I have one arrow here, alpha. I give myself one linear map for this. I have another arrow, beta. I give myself one linear map for that. No conditions. That's all. Just I literally represent every arrow. Every arrow is represented by one linear map. Okay. I come back to the transitivity in a second. Yeah. Then the maps need to commute. Yes. Yeah. Yeah. That adds some more information to the quiver representation. Yeah. Yeah, but let's come back to this in a minute. It's more general than a representation of a poset. Not every quiver is the Hasse quiver of a poset. Yes. Every finite poset gives me a Hasse quiver, but there's more quivers than that. And the notion of a quiver representation here is very easy to define. Just replace every arrow by a linear map between the corresponding vector spaces. That's it. No conditions attached. That's why I started with this one. Let's now go to a representation of a poset. Okay, so what is, if I have a poset P and I fix myself a field K, I I want to define the category of representations of the poset. So this time I want to do the same thing. Yeah, I want to have a function, a map M that goes from the poset to vector spaces. I want to replace every point by a vector space Mx. Yeah. And now the poset structure, so the relation x is smaller y, should be represented by a linear map between the corresponding vector spaces. So for every poset, for every order relation x is smaller y, I give myself a linear map mxy that goes from mx to my. Okay? Now I wrote the word functor. Okay, so if you go to the TDA papers, persistent theory papers, they define the category of representations of the poset P as the category of functors M from P to vector spaces. For a functor, I need a category. So for the experts, I can view my poset as a category. The objects are the points, and I have one morphism. If x is smaller y, I have one morphism from x to y. If x is not smaller than y, there is no morphism. And then I can describe this M as a functor. What does that mean as a functor? That means for every relation x smaller y, I give myself a linear map. So x is smaller than itself, reflexivity. So I insist that this linear map mxx from mx to mx is the identity map. This is a condition. And coming back to your transitivity, when x is smaller y and y is smaller z, then I do know that x is also smaller z. And then I have these two maps, x, y, and y, z. I can compose them, and I do insist that I do get that map from x to y, x to z, okay? So transitivity of the poset encodes that the composition of these two linear maps must be this one, yeah. So in this sense, representations of posets are a little bit more complicated to formulate, but it's all included in the language that M is a functor. This condition here just means M is functorial. Okay? Good. And we didn't need that for quivers, yeah? So when no, example. Let's look at an example. So I have my poset P, which is the poset of 3 points. 1 is smaller, 2 is smaller, 3. Okay? I give myself a representation of this poset. The representation is given by 3 vector spaces, 1 for 1, 1 for 2, and 1 for 3. K square K. And linear maps for this order relation 1 is smaller than 2. I give myself this linear map, and 2 is smaller 3. I give myself that linear map. Now for a representation of posets, there's a bunch of other linear maps that I'm supposed to give you. For instance, M11 is the identity on K, is M33, and M22 is the identity here in the middle. And then there's this linear map from 1 to 3. The linear map from 1 to 3, you can compute yourself. I mean, the linear map from 1 to 3 must be the composition of these two maps, yeah? And you compute the composition of these two maps, this gives you that linear map, okay? So kind of you see that the linear maps that are there by transitivity of the poset, they are just the composition of the linear maps that correspond to the arrows in the Hasse diagram. So I kind of don't need them. I don't need to store all this information, yeah? So let's formulate this as a fact. I mean, mathematicians are trained to certain keywords, theorem, proposition. I wouldn't call this a theorem or a proposition, and I wouldn't know where this is written anyway. So let's call it a fact, okay? So when I have a finite poset and I have the Hasse quiver of this finite poset, then I can do two things. I look at the representations of the poset, or I look at the representation of the quiver. And as we just discussed, It is sufficient if you have the data for the quiver, then you close it by transitivity, you include all the compositions, then you get the thing on the left-hand side, yeah? So if you look at the category of representations of the poset or of the quiver, the Hasse quiver of the poset, it's going to be the same thing. These are equivalent categories. We can do either of the two. Yeah. No? A poset by definition, one can be smaller than three only in one way. It's not made, it's not encoded into the order relation that one cannot be in two ways smaller than three. Yeah. So for this poset, yeah, this is very good. So for this poset, we have to insist that we have a commutativity here. So when I go from 1 to 2 and from 2 to 4, and I compose these two maps, this gives me a map from 1 to 4. I could also go from 1 to 3 and from 3 to 4, I compose these two maps. But since I'm in a poset, I have only one map from 1 to 4. So this composition must be equal to this composition. This is an condition on the quiver representation. If the quiver is the Hasse quiver of a poset, then I need to insist that any two paths will commute. Okay, that's good. Now, this is an important point. Thank you for pointing this out. Thank you very much. Okay, good. So we have that. We can go to representations of the Hasse quiver, and we insist they come with commutativity. For parallel paths. That's okay? Okay, good. Thank you. So we can go back to our original picture. Our original picture, yeah, we had this beautiful diagram. We start with the finite data set, then we get the filtered system. And for every pair of radii, epsilon and epsilon prime, we get the inclusion. So we compute this linear map, okay? So we do get, in fact, for every point, for every real number, we do get a vector space. And for every order relation, we do get a linear map. So we get a representation of that poset. If we also notice what I didn't tell you, that the homology of the identity homology preserves identities. Yeah, I mean, if epsilon and epsilon prime are equal, then the homology linear map will be identity map, and homology is functorial when I have three different epsilon values and I compose the corresponding two maps, I get the third map. Yeah. So homology is a functor. It automatically satisfies the conditions that we need in order to be able to say this is a representation of a poset. Yeah. So I didn't write this before. Maybe you were assuming it automatically. This is what we have. Okay. So really, homology is a representation of the posets, the real numbers, the non-negative real numbers. Okay. Good. Question? Remarks. So first thing, when we start with a finite data set D, then there will be only finitely many values of epsilon where the homology is going to change. Yeah, I mean, we have seen this here that for most of the time I can change my radius, but no two components will merge, no circles will appear. I mean, for most of the time, nothing happens to the topology, right? I mean, there's a very few discrete time steps. Now something has happened, yeah. Then we go, something more has happened. So there's a finite number of epsilons where the homology, where the topology changes. okay? Therefore, it is justified to focus on those finitely many values where there's some change in the homology. And then I'm back at my quiver representation, yeah? Instead of all the real numbers, I only look at those finitely many values, and I get a representation of a quiver, which is of type AN, and I'm very happy. That's good? Second remark, this, as I said, this was only one construction, which is called one parameter persistence theory, because we vary one parameter, the radius. But in general, you could also, you might want to consider bifiltrations of topological spaces that depend on two parameters. One parameter could be the radius epsilon. The other parameter could be something like a density parameter in order to filter out noise or something. And then you would get something like R squared as a poset, or maybe the discrete version would be such a discrete grid. Yeah. If I do the same game as I did here, there's only finitely many values where the homology changes. We would have such a finite grid, which is a part of R2 as a poset. So these are all very valid posets that should be looked at. Okay. Shall I go back to the this thing here? We said that what if I have an outlier here? Yeah, I mean, if one point is very far away here, okay? Then the thing still works relatively well. I mean, I still see my non-contractible circle. I still see an H1 appearing here, and the outlier is here on the side. This doesn't change the picture at all. Yeah. What is very critical is if that outlier would be kind of sitting in the middle. Yeah. If I do that, then it messes up everything, and for that reason, you want to filter out a noise in the data by having a density parameter. So you have kind of a density and a radius. It's kind of beneficial to look at two parameters in some cases. Of course, everything becomes more complicated if you have two parameters. And I would like to discuss from the representation theory what becomes more complicated, and also computational, everything becomes more complicated, that's for sure. Yeah. Okay. Questions so far? And when we are, so final remark for the one parameter persistence theory, we have a representation of this quiver of type AN. Now I tell you, those representations, they are well known. They decompose uniquely into a set of indecomposable representations that we know very well. Every indecomposable representation of a quiver of type AN is given by an interval, I mean by two values A and B between 1 and n. And over that interval, I put one-dimensional vector spaces, KKK, and 0 outside. So this is kind of what they call an interval module, KAB. M will be decomposing as a representation into a direct sum of those guys. And then the indecomposable decomposition completely determines the module. So the only thing I need to know about M is the collection of those intervals. So I can draw them in a kind of a scheme. So A, B, and all the intervals. This is what is called the barcode. Yeah. And the long intervals, they correspond to features that persist longer. This is the ones we are interested in. Yes. Yeah, I'm cheating here. So any given data set will have only finitely many values of a radius epsilon where something changes, and then I focus on those finitely many values, because in between everything will be isomorphic, nothing changes, there's no relevant information there. So this is kind of an epsilon1, an epsilon2, and an epsilon n. Only at those finitely many points I'm gonna look at. Okay? And so that's why I can view the whole thing as a representation of a quiver of type AN. Yeah. And the two parameter case, the representation category is what people call wild, and it should just tell you such a simple decomposition into composables which I can control and which I can draw. Such a thing does not exist. Yeah, so from the representation theory already, the two parameter case is a lot more complicated than the one parameter case. And I will certainly not do that today, but for a lot of what comes now, I would like to give you we didn't talk about not what is a direct sum. We didn't talk about what is an isomorphism or a morphism between representations. Let's talk about this. Okay, so I'm gonna start. I will not finish today. I will continue tomorrow. Okay? Yeah, so questions so far? Yeah?
When you do epsilon1 and epsilon n, would you take epsilon n plus 1 equal to infinity?
Yeah. So often in the persistence diagram, they label one parameter as infinity. I mean, this is kind of, if I'm large enough, then the situation doesn't change anymore. I mean, if my radius is what, 6.5 or infinity, it doesn't change at all the homology H0. Yeah, so you can just label it infinite.
At some point you have isomorphism.
Yeah. At some point, everything becomes isomorphic, and I can label this infinite or whatever. Yeah. Here it's labeled 15. 15 is infinite here. Yeah. But I mean, I starting for H0, I mean, starting here, no, it's already connected here. Starting here, nothing changes for H0. You can stop it. You can go to infinity. Doesn't change. Okay. Okay, good. How much time do you give me? 5 minutes? 5 minutes. Okay, so let me start. So I really want to do those things now in detail. What is a direct sum? We defined representations. They are linear maps. What is a direct sum of a representation, and so on and so on. Okay. So let me start doing this, and then we continue tomorrow. Okay. So given two representations of a poset or of a quiver, they are given by a bunch of linear maps. It's completely the same story. So given two representations, I want to define what is the direct sum of M and N. So the direct sum is given by the following. A representation, I need to specify what happens at each point. So at each point, I take the direct sum of the vector spaces. And then I have those maps between the vector spaces. So if I have x is smaller y, then I need to define a map from the direct sum of the two vector spaces at x into the direct sum of the two vector spaces in y. And I just take the two maps which I have, because I do have representations. So I have a map from M, I have a map from N, and I just put them in the diagonal and zero outside. Then I call this the direct sum. Okay? Good. Not good. Let's do an example. Example, this is my quiver, which is also my poset, because it's the Hasse quiver of this poset. I've got my representation M here. I've got my representation N here. I want to do the direct sum. So I sum up k plus k squared. This is k cubed. Same here, k cubed, k plus k is k squared. And then I need to just place these linear maps, not not delete them, place them in the diagonal positions here, and I get my direct sum. You see what we do? I take this linear map and I put it here, and this linear map, I put it there, and I do the same thing for the other representation. I take the linear map in the diagonal position. No, not the linear map. I wanted to take a copy of the linear map and I put it there. And this is my direct sum. So you really see, you put as building blocks, the two representations, you put them in the diagonal and you fill it up with zeros outside. That's good? We got that? Okay, perfect. Then you can do it now. Now it's your exercise, okay? You're ready. This is a school, summer school. Okay, you ready for this? Let's make it easier. Let's make it easier. So my representations become smaller now. You see what I have? I have a representation one-dimensional, zero-dimensional here, okay? The linear map into, I mean, this can only be the zero map, okay? And the other representation, n, is also very small. I have a zero-dimensional space, a one-dimensional space. The only linear map would map 0 to 0. This is the zero map. And I take the direct sum. So now you help me. So I take the direct sum of the vector spaces. K plus 0, this is one-dimensional, okay? K plus K, this is two-dimensional, and 0 plus K, this is one-dimensional. Okay, good. And then I just copy the matrices diagonally into the appropriate places. Good. I copy, right? Do you want to help me? I mean, I copy this map here. I can do that. I copy the map here. This comes here. That's what we did, right? And now this is the million-dollar question. What is the matrix of this map? Yeah, no, we need to be a little bit more specific here. I mean, linear algebra. We are based on linear algebra. That's what I said, right? So a linear map from k to k square is given by a matrix of which dimension? How many rows? 2 rows, 1 column. Okay, 2 rows, 1 column. You agree with this? Okay, maybe you didn't do that in linear algebra, but a map from K1 to K0 has how many rows and how many columns? It has 1 row and 0 columns. That's very logical, right? No, but it has to be. They didn't tell you in linear algebra? But it must be, right? I mean, there's a 1 row and a 0 column. Let's draw it like this. You agree? So I have a little map which has no row, but it has definitely got 1 column, and I copy this one here. You see what I do? Okay, excellent. I have another map here. This linear map over there has, so this one has how many rows and columns? Perfect. It has got 0 rows, no rows, and 1, what? The other way around. Yeah, the other way around. So this has got a column because it goes into K, but it has got no rows because it starts in 0, right? So you see my matrix here. So I copy this matrix here. You see what I do? And I copy I copy the actually honest matrix which I have. I copy here, and then I fill the off-diagonal entries. I fill the off-diagonal entries with zeros, and I got my direct sum. This is how it works. That's good? Okay, so we do understand direct sums. Maybe I stop here with this little exercise on linear algebra. Thank you very much.